Hi guys, good morning. You guys are ready? Shall we start?
Yes, sir.
Yes, sir.
Ah,
Yes, sir.
cool. Right. So we were looking at molecular orbital theory, isn't it? So I just gave you a few introduction, right? So I told you that I'm going to have atomic orbitals along with their wave functions, right, combining together to form molecular orbitals, right? So there can be two types of molecular orbitals. One is what is called as bonding molecular orbitals. The other one is what is called as anti-bonding molecular orbitals, right? So we know how they are formed. We saw something called as constructive interference and destructive interference, like waves, how they interact can be of two types. Like say the crust and crust, or the trough and trough will interact to make a bigger wave, and that is my constructive interference. And say destructive interference, the crust and the trough will react to form a smaller wave, and that is my destructive interference. So whenever you have constructive interference, bonding molecular orbitals are formed, and whenever you have destructive interference, anti-bonding molecular orbitals are formed, right? And then we will look at the shapes of different molecular orbitals, right? So hope you can understand that if at all I'm going to have destructive interference, I'm going to have a nodal plane, right, which is perpendicular to the mm, internuclear axis. And if it is going to be a pi bonding orbital, right, if it is pi 2px or pi 2py, right, I told you that I'm going to have one parallel, and if it is going to be pi star, I'm going to have one more. There are going to be two nodal planes if I'm going to have pi star, right, anti-bondings of pi, right, we'll have two nodal planes, right? So all these we saw, and then I told you that this is how, like, all the laws which you follow for filling atomic orbitals, that is electrons in atomic orbitals, that is by Aufbau's principle, Pauli's exclusion principle, what to say, your Hund's rule of maximum, right? All these has to be followed here also, right? And then I gave you an order in which you which you have to fill it, starting with sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, so pi 2px equal to pi 2py. So, okay, I'll write it again for you, right? So I told you there are going to be two types of configurations, right? So one, when I have the total number of electrons in the molecule, please understand. Now when I talk about electrons, it is not about the electrons in an atom. We're talking about electrons, total number of electrons in a molecule, say H2, Cl2, O2, right? So these kind of molecules, total number of electrons has to be taken. And for that, I told you, if the total number of electron is less than 15, this is how the order is going to be: sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px equal to pi 2py. Then you have your sigma 2pz. Then you have pi star 2px equal to pi star 2py. And then I have your sigma star 2pz, right? So this is the order in which you're going to fill the electron, and obviously each of these molecular orbitals can have two electrons. That's it, very simple, right? Now there is no question where, sir, I have p orbitals to have 6 electrons. Yes, pi orbitals will have 6 electrons, but the thing is, you have taken like separated them into px, py, and pz, and you took z axis as the internuclear axis. So your sigma bond is formed by your pz, and pi bond is formed by px and py. You can see here px and py is forming pi bond, and your, where is it? Sigma is formed by pz, right? So obviously all of them, each one of them can have a maximum of 2 electrons. That's it, that you have to know, right? Okay, so now we are going to see something called as molecular orbital diagrams, right? Say this is what is called as your MO diagrams, which is very simple. Like, we're just going to show you how we are going to fill the electrons, and this can be a very good question. This can be a question which can be asked in annual exams. It's very simple only, right? Now we'll take a very simplest of molecules, right? And we'll try to fill in the electrons here. Okay, fine. Let me take hydrogen. That is the simplest of molecule I know, right? Okay. And I forgot one more thing. If at all the number of electrons is greater than 15, the only thing which you have to change is these two, right? Your sigma 2pz will come first, and then your phi 2px equal to phi 2py will come. That nothing else will change. So that alone you have to make sure. Fine. So we'll take H2 as an example. Okay, you can change my marker. Right. So I have two hydrogen atoms. Right. So I have an hydrogen. I have this is my 1s, one more 1s, and I know each of them will have 1 and 1 electron. 1s1 is the configuration. Hydrogen have atomic number of 1. Right. So I have 1s1s. Right. Okay. Now they are coming together. These two atomic orbitals will come together to form two molecular orbitals. One is your bonding molecular orbital. The other one is going to be your anti-bonding molecular orbital. And I already told you, right? So when I say bonding molecular orbitals, that means they are going to favor bond formation, right? They are going to favor bond formation. And if it is going to be anti-bonding MOs, that is molecular orbitals, it is going to oppose bond formation, right? So when I talk in terms of stability, right, obviously whichever say favors bond formation will have more stability, because I know why a chemical bond is formed in the first place, right? I know chemical bond is formed because I need to have stability in the molecule. The atoms involving in the bond formation are going to attain stability, right? So obviously bonding MOs will have lesser energy when compared to your anti-bonding MOs, because I told you stability and energy are inversely related. Higher energy, less stability. Less energy, more stability, right? So bonding MOs will have high stability, less energy. Anti-bonding MOs will have more energy, less stability. This we have to know, right? So now if, for example, in this y-axis I put energy, just indicating how the energy values are varying, right? So I can say that first these two will combine, right? So from the first molecular orbital, and that is my sigma 1s. You can see 1s orbital is combined to form sigma 1s, right? And obviously now you can see this is lesser in energy, right? Now obviously when they combine the other way, right? Now they are going to form another molecular orbital, that is my sigma star 1s, right? Okay, that's it. Now this is what is going to get formed. Cool. Now I have to fill the electrons in this, correct? So now I have totally two electrons, one electron coming from each hydrogen, and I told you that you have to follow off-cost principle. So obviously sigma 1s is having lesser energy. You will directly put two electrons here. Very, very simple. Right? And there are no electrons in sigma star 1s. Understood? Right? Now guys, everybody understood how am I doing it here?
Yes, sir.
Okay, cool. Right. So we'll take another example. We'll take another example. So this is for H2, very simplest of the one. Right. So let me we've taken this down, hopefully. Right. So let me take say B2 molecule, boron 2. Right. So I know boron has an atomic number of 5. So B2 will have total number of electrons to be 10. Right. Okay. So I'll write the configuration first. Boron will have 1s2, 2s2, 2p1. No problem, right? Okay. So boron here and another boron here. Now starting with this, right? So boron will have first 1s2, right? So in 1s, I'll still go down actually. So 1s2, this is my 1s2, 1s2. So fine. So first, these 1s orbitals will combine to form two molecular orbitals, sigma 1s and sigma star 1s. Again, sigma 1s will have lesser energy. And that, okay, first we'll make this, then we'll go for the So this is my sigma 1s, this is my sigma star 1s. Okay. Now in 1s orbital, I have totally what? 4 electrons. 1s, two electrons coming from boron, each boron, right? So I have 4 electrons to fill here. Directly you can put two electrons. No problem, right? Okay. Next, what is there? 2s is there. Okay. So now 2s. Again, I have 2 electrons. Okay. Now they will combine again to form 2 molecular orbitals. That is my sigma 2s. And next is my sigma star 2s. Right. So again, how many electrons? Two electrons. Done. Right. So now what is left out? 2p1 and 2p1 are left out. Right. So I don't know space. Where will I write it? Okay. First, take this down. This is done. Actually, this should be a very big diagram. Right. So you have to show 1s, 2s as well as 2p. But now I don't have space, so I'm rubbing this part. Please take this down, the 1s part. Right. Can I rub this?
Yes, sir. Yes, sir.
Okay. So what is left out is 2p1. In 2p, I have 1 electron. In another 2p, also I have 1 electron. So now this first will form what? I told you the order. And if it is basically it is going to be 2pz. That's what you're going to take because sigma is going to get formed first, right? So now I'll have, okay, this is my sigma 2pz, and I have sigma. Wait. See now, right? So p or okay, actually I'll rub this also. How are you going to do about p is the question. So now let me mark it actually. So actually now the sigma star 2pz is not going to be here, isn't it? Right? Because why? After sigma 2pz in the energy this thing that Aufbauer's principle I told you. After sigma 2pz what comes? Pi 2px equal to pi 2py comes. Then you have pi star 2px, pi star 2py. Then only sigma star 2pz. Are you able to understand? Right. So after this, what I'm going to have is 2 orbitals of equal energy. That is my pi 2px equal to pi 2py. And also, I have your another 2 orbitals which are going to be pi star 2px and pi star 2py. Still, I have one more, and that is my sigma 2pz, sigma star 2pz. Done. Right? This is how you have to do for the p orbital. Okay. So first is sigma 2pz is having least energy, then your pi 2px equal to pi 2py, then pi star 2px and pi star 2py, and lastly only sigma 2pz, sigma star 2pz. Okay. So anyways, now I have to fill totally 2 electrons only, so there is no problem. I can directly go for putting 2 electrons here. That's it. Or all the other orbitals are empty. Okay. Right. Cool. So now if it was C2 molecule, like instead of B2, if it was C2, right? Instead of B2, if it was C2 molecule, right? Now carbon is having the atomic number of 6. So totally how many electrons now? 12 electrons, right? So again, I will have sigma 1s, 1s2, 2s2, 2p2 instead of B, correct? Right? So 1s and 2s, similarly, we saw exactly same thing. If it is going to be the, say, extra 1 electron is here, so it is not 2p1, it is 2p2 here, right? Now what I'm going to do, I'm going to have this filled, right? And when I come here, you cannot directly put 2 electrons in one orbital. Why? Why?
Hund's rule.
Exactly, right? So Hund's rule says, if at all you have orbitals of equal energy, right, you have to singly fill them first and then only go for pairing, right? So obviously what I have to do, I have to put 1 electron and 1 electron here and here. And again, all the other things are empty. Understood? Right? Cool. Now, like this only we'll do. Say I'll take one more example. Now I'll take an atomic number, total number of electrons to be greater than 50, right? So let me take O2 molecule, right? So if I take O2 molecule, I know something will change. What will change? Now this, what will change? This and this will change, isn't it? Right? Sigma 2pz will come after phi 2px and phi 2py. Am I doing, oh, guys, we are doing something wrong, isn't it? What are we doing wrong?
For O2, sir.
So B2 itself, we did something wrong. What we did wrong? For B2 itself, we did something wrong. What was that?
So for 2p, we filled 2 electrons, sir.
No. Thing is, if you look at the order, it's actually sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. First comes your phi 2px equal to phi 2py. Then only sigma 2pz comes. But what did we do here? We
We
put
put sigma 2pz first.
So entirely wrong, right? So let me change it. You also change it, please. Right? So first I need to have 2 orbitals here, right? Pi 2px and pi 2py, and here I'm going to have sigma 2pz. Okay. So if it is B2, right? If it is B2, I'm having only one electron here. So now how should I put it? Again, I have to follow Hans' rule. Like I have to put the electrons here only. So it's 1 and 1. Done. Right? Then if it is C2 molecule, right? Then if it is C2 molecule, I'm going to have 2p2 and 2p2. So now I have to go for pairing. So here I will get this again, all the other orbitals, right? So please make the changes. Please ensure that if it is the total number of electrons is less than 15, phi 2px and phi 2py should come first. Then only sigma 2pz. That mistake we did here. We corrected. Okay, right? Cool. So now let me take examples where the total number of electrons is greater than 15, right? So let me take the example of O2, oxygen molecule, right? So I know O2 has oxygen has atomic number of 8, right? So total number of electrons will be 16, correct? Okay, but again I have to change this, is it not? Because I know if it is going to be greater than 15, I know what will change. I know this and this will change, interchange their position. Rest all are same, right? So now let me take an example as O2. Example of O2, the total number of electrons is 16. And if I write it 1s2, 2s2, 2p4.
Sir?
Yeah.
Sir, this is Surya Muthu, sir. I came a little late because I had some network problem.
Okay.
Also, sir, it shows that I got 0 in my chemistry test.
I didn't see your paper, Surya.
You didn't see my paper.
Yeah, that's why. If I have corrected the paper, it would have gotten maybe instead of absent, they would have given 0.
Actually, I wrote the test, sir.
You wrote the test?
I wrote the test, sir. I even submitted it.
Oh, can you speak with Akila, ma'am? She will
Okay.
Know.
Okay.
Right?
Okay, sir.
Right? And if she gives me the paper, I'll correct and give it to you back. No
okay. Okay, sir.
Okay. Yeah. Cool. So yeah. Okay, now instead of writing it like this, people, instead of writing a 2p4 like this, let me write it like this. Okay, so in 2p4, I know how I'm going to fill, isn't it? Say a 1, 1, 1, and then this is my, say, let me take it as pz, px, and py. Because I know sigma is going to get, or I can even keep it px, py, and pz, whatever it is. Okay, right? Cool. So first we'll change this. Okay, so let me take it as okay, first in this case it will change, right? Let me put it as pz only. But guys, you don't have to worry what I'm doing here. Okay, so this is my 2pz first. Okay, So 2pz, I know if it is greater than 15, the first thing which will come would be to sigma 2pz, right? And actually, you should not be writing it like this. Okay. So this, okay, basically for sigma, so 2pz orbital, you have sigma 2pz and sigma star 2pz. And after that, I have your px and py also. This is my px and py, 2px and 2py, right? Now, how many electrons they are having? They are having 1 electron each. Same way, this is my px, py, having one electron each, right? Now, what is going to happen? I am going to have these two coming here to form pi 2px and pi 2py, and again they will come together to form pi star 2px and pi star 2py, and from this it goes to sigma 2pz. Okay, if at all I have some other color, I can mark it. So this goes here and comes here, same way goes here, and for these two, this goes here, and this comes here, and this comes here. Like I don't have a proper marker, I'll write. So anyways, so please understand that pz and pz will combine together to form sigma 2pz and sigma star 2pz. And px and py will combine together to form pi 2px and pi 2py and pi star 2px and pi star 2py. This has to be shown, people. You cannot just show p orbitals and then go for it. Like last time we didn't show this because there were only one p orbital filled. 2p2 was the configuration. Understood, right? So in this case, I have all the p orbitals filled, px, py, and pz. So this is how you have to show. But the energy order should be similar. Please understand the energy order. I'm not changing the energy order, right? So please understand that. Okay, cool. Fine. So I have 2 electrons here, right? Again, one electron in px and py. I have marked it, right? One electron, 2 electrons, 2 electrons. Done, right? Now let me fill the electrons. Now these 2 electrons, okay, there are 4 electrons I have to fill from this. So it would go here, and then you have okay, pi, okay, 2 more electrons, 1 and 1, and then again I have to pair now. Done, right? And how many electrons are left? Totally, how many electrons P has? 4 electrons. Totally 8 electrons. So 1, 2, 3, 4 twice. Totally 8 electrons. Now how many have accounted for? 1, 2, 3, 4, 5, 6 electrons I have accounted for. So 2 more electrons I have to account for. Obviously I have to go here now, right? So here if I go, obviously I have to put 1 electron here, another electron. So pi star 2px1 and pi star 2py1. This would have been the configuration. Guys, any doubts you have, please ask me, because I know it is little messed up, right? So do you have any doubts, or I'll explain again? No problem. Okay, fine. So I have oxygen molecule O to have 2p4. 1s2, you have to include here, people. It's not only about the valence shell. You have to include the previous shells also in the orbital diagram. Then only you'll get the full marks. Again, I'm repeating. Okay. So I have 1s2, assuming it is already done. Now I'm going for 2p4. So 2p4, you should write the 3 orbitals like this: px, py, and pz. Px, py, and pz. Right? Again, the order in which they have to fill, off course principal order, has to be known. Sigma 2px, 2pz, pi 2px, pi 2py. Now actually this is changing here because the total number of electrons is greater than 15. So actually, if it is not, this would have come down and this would have come up if it is less than 15. Anyways, so now after this pi star 2px and pi star 2py, then your sigma star 2pz. Right. So totally in p orbital, I have 4 electrons each. Totally 8 electrons to be filled. 1, 2, 3, 4. 1, 2, 3, 4. Totally 8. So first I'll put the 2 electrons here. Then 1 electron, 1 electron, 1 electron, 1 electron. Totally 6. So 2 more electrons left out, and that will go to 1 orbital of each of pi 2px, pi star 2px, pi star 2py. Understood? Any doubts?
No, sir.
Okay. Cool. Right. So this is how the orbital diagram has to be filled. Okay, but only for your school it's important, right? But if you go for any competitive exam, this orbital diagrams are not that important, right? So we can directly write the configuration itself in terms of your orbitals. You don't have to fill it in here and show it, right? So anyways, cool. So we'll do it. We'll go for the configuration of this. How do we write the configuration there? And from there, we'll be able to get a lot of information that we'll see how to do. Okay. So hope you've taken this down. Okay, fine. So for whatever the molecule we did, now we'll write the configuration in terms of the sigma 1s, sigma star 1s. How you write 1s2, 2s2, like that. We try to do it here. So now for H2 molecule, I know the total number of electrons is 2, right? So now how will write the configuration? Sigma 1s2. That's it, right? So now then we saw B2 molecule, which is having 10 electrons, right? Now how will I write it? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, totally 8 electrons, 2 more electrons. Now, which has to come first? Your pi has to come first because it is having lesser than the 15 electrons. So pi 2px equal to pi 2py, each having 1 electron, right? Then if it was C2 molecule, which is having 12, everything would have been same, but it would have been pi 2px2 equal to pi 2py2. Now the pairing would have happened, right? Now say if I went for O2 molecule, right? So I have totally 16 electrons. So sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Now what comes? Sigma 2pz comes first. You can see the difference here. Sigma 2pz2. Now totally 16 electrons. So 1, 2, 3, 4, 5, 6. Then you have pi 2px equal to pi 2py. So 1, 2, 3, 4, 5, 6, 7. Actually, I should put 1, 1, then 2, 2. Anyways, it's fine now, right? Then you have your pi star 2py 2px equal to pi star 2py. So now 2 more electrons are left out. So I'll put 1 and 1. This is how you write the configurations. Very simple. Whatever you saw in the form of a diagram, we are seeing in the form of the configuration, the electronic configuration in terms of molecular orbitals. Okay, right? Fine. So now this you fill. This is easy, right? The only thing which you have to remember is the 2 configurations, one lesser than 15 and one greater than 15. If you can remember, everything is very, 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 very easy. Orbital diagram is also very easy, except that it is going to look very big, but you saw how easy it was, right? Okay, cool. So that is about how are you going to fill the electrons in the orbitals, molecular orbitals, right? So now I'm going to introduce you to certain terms, right? So I told you that with there are so many problems we faced in your DSC PR and theory of hybridization. Say for example, there was no insight about the magnetic properties. Say if I bring a magnet near a particular molecule, it may attract or it might repel or nothing will happen, right? So those things, why it happens and all are not explained, right? So to some extent, even color, like why certain molecules are colored, why certain molecules are not colored or not explained. And the next thing is the stability of molecules, right? So whether the molecule is stable or not, whether the molecule exists or not, right? They can draw so many structures, but whether the molecule exists in reality, all these things your VSCPR and theory of hybridization doesn't say, right? But with the help of your MOT, you can actually overcome most of the problems you face in VSCPR and theory of hybridization. The first one is you will be able to find whether the magnetic properties, right? So you'll be able to find about the magnetic properties of these elements. I'll tell you what all the magnetic properties, but I'm telling. So with this, you'll be able to predict the magnetic properties. Color, no. Color you will not be able to predict. With this, you'll be seeing how do I predict color when I go for 12th. Right, there is a chapter called as coordination compounds. So at that time I explain you, right, how are we going to decide whether that particular molecule will be colored or not. We'll be able to predict what color will not be able to predict, but whether it will be colored or not, yes, we'll be able to predict, right? So not now, but right. So first thing is it will be able to predict your magnetic properties. Second thing is it will be able to tell whether the molecule exists or not, right? The molecule exists or not, will be able to tell. And third thing is it will be able to speak about the stability of different species, right? Stability of different species. Okay, cool. Right. So we'll move on. So I'm going to introduce you to certain things here. Right. Okay. So there is a thing called as bond order. Okay. So it's nothing big. Okay, just a formula, right? And indirectly, this tells you how many bonds are formed between the two atoms. Say for example, H2. I know between the hydrogen atom there is only one bond. If it is O2 molecule, I know there are going to be two bonds. If it is N2 molecule, I know it is going to have three bonds, triple bond, right? So basically, bond order explains how many bonds are going to get formed between the two atoms. And obviously, it is going to talk about stability. And if I know stability, I know the bond strength, right? And I know if I know bond strength, I will be able to predict bond length, right? So all these things we'll be able to do. Okay, fine, cool. So bond order BO is equal to, it's the formula, very simple formula, right? It's equal to half into number of electrons in bonding molecular orbital. If I write BMO, BMO is bonding molecular orbital, right? Minus number of electrons in anti-bonding molecular orbital, right? So it's a very simple formula, half, that is 1/2, into number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. Okay, we'll take some examples. Say for here hydrogen, I had sigma 1s2, that's it, right? So now if I put into the formula, bond order in this case will be half into, there are two electrons in bonding orbital, that is sigma 1s, right? And there are no electrons in anti-bonding, so 0, right? So 2/2 will become 1. So you can see, right? It shows that hydrogen will have only one bond, single bond. Bond order is 1. Okay, so let me take nitrogen molecule. We'll see what happens there. Okay, so it is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Now it is less than 15. So I'll write pi 2px equal to pi 2py. How many over? 1, 2, 3, 4, 5, 6. Actually, again, I have to put 1, 1, then 2, 2. So 1, 2, 3, 4, 5, 6. Only one is left. That is my sigma 2pz2. Totally 14 electrons I have. Nitrogen has atomic number of 7. So totally 14 electrons. No problem. Okay. Now if I go for the bond order calculations, right? So again, half into. Now I have to calculate the total number of electrons in bonding orbitals, bonding molecular orbitals. So it's 2, 4, 6, 8, 10. No problem. Whatever doesn't have star, that's my bonding orbitals, right? So 1, 2, 3, 4, 5, totally 10 electrons are there, right? And how many are there in your anti-bonding? So here and here, I have your anti-bonding, totally 4 electrons. 10 minus 4. So 10 minus 4 is 6. 6/2 is 3. So you can easily see that nitrogen molecule, and between nitrogen, there are going to be 3 bonds. The bond order is 3. Understood? Right? So like this, you will be able to find the bond order. Very, very simple calculation. Half into number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding molecular orbitals. So if you do the electronic configuration correctly, right, and bond order calculation is very, very easy, right? But if you screw up here, that is in the electronic configuration, then nobody can save you, right? Okay, so that's about bond order. So bond order, I told you, is going to speak about how many bonds it is going to have, that particular molecule is going to have. No problem. Okay. Now, I told you with the help of bond order, we'll be able to speak about stability. We'll be able to speak about bond strength. We'll be able to speak about bond length. So all these things we'll see. Right? So obviously what you can understand is, more is the number of bonds, or say more is the bond order, can I say the bond strength is increasing? So I obviously know a double bond is stronger than a single bond. A triple bond is stronger than a double bond. All these we already know, isn't it? So obviously, like I would say, more and more the strength of the bond, more and more the stability of the molecule. All these things will be able to connect, isn't it? So now with bond order, I'll be able to easily connect two or more things with this, right? Okay, so our bond order is directly proportional to the bond strength. Please know this first, right? Bond order is directly proportional to the bond strength. Just now we spoke. Like a double bond is stronger than a single bond, triple bond is stronger than a double bond, right? And obviously, if the bond strength increases, obviously stability of the molecule also increases, right? So my bond order, I can say, is directly proportional to stability also, right? And I can even speak about bond length, right? So if I have the strength of the bond to be very, very high, right? So what will happen to the bond length? That means the atoms are very, very, very close to each other, correct? So obviously my bond order is going to be inversely proportional to the bond length, right? So these three things you have to know. Okay, so bond order is directly proportional to bond strength, obviously directly proportional to stability, and if the bond strength is higher, bond length is lesser. So bond order and bond length are inversely related. Okay, these things you have to know. Okay, cool. So sometimes what will happen is, okay, let me give you a question. Okay, so I want you to tell me, I have Li2, Li2 1 plus, Li2 1 minus. Okay, so I want you to arrange them in the order of stability. Go for it. I'll give you 2 minutes. Quickly go for it. Li2, Li2 1 plus, and Li2 1 minus. Go for it. I want you to arrange them in the order of stability. So the moment stability asks, what will you do? Calculate, write the electronic configuration of all of them, and then go for your bond order calculations. And whichever is having the highest bond order will have highest stability, so that you'll be able to arrange. Now, do not worry about the signs. You know what it does. So Li2 is neutral. So totally, lithium has an atomic number of 3. So totally 6 electrons here. Here, how many electrons? Li2 1 plus. I think you're doing the problem. So obviously here I have 5 electrons. Here I have 7 electrons. So plus means what? 1 electron removed. 1 plus means 1 electron removed. So totally 6 from Li2. 1 electron removed will become 5. Li2 1 minus means 1 electron is added. So obviously 7 electrons here. Go for it. Okay. Did you find anything strange, people?
Yes, sir.
What did you find?
For Li plus and Li2 minus, I'm getting half, sir.
So both of them are having same bond order, isn't it?
Yes, sir.
Okay, fine. So anyways, we'll see what we have to do about it. But let me write the configuration. So it's 6. So it's sigma 1s2, sigma star 1s2, and your sigma 2s2, right? And if it is, okay, let me calculate the bond order here. Half into total number of electrons in bonding. So 2, 4, 4. And there are 2 electrons in anti-bonding. So 4 minus 2 is 2. 2 by 2 is 1. Bond order is 1. Okay. So now I have for Li2 1 plus, I would have had sigma 1s2, sigma star 1s2, and sigma 2s1, not sigma 2s2. There are only 5 electrons, right? So now I have half into 3 electrons in bonding orbital, 2 electrons here, 1 electron here, and 2 electrons in anti-bonding. So you'll find the bond order to be 0.5, right? And here it is sigma 1s, sigma star 1s, sorry, sigma star 1s, sigma 2s2, totally 6 electrons, so 1 more electron, so sigma star 2s1. No problem. Okay, if I calculate the bond order, half into 2, 4. 4 electrons, and there are 2 plus 1, 3 electrons. So again, it's going to be 1 by 2, which is 0.5. Okay, right. So here you see, obviously the maximum stable of the mole is going to be Li2, no doubt, because that is having a bond order of 1. The other two are having bond order of 0.5 and 0.5. Okay. So in these times, how will you decide the stability? Is the question. Take a note. Note. If the bond order is same, if the bond order is same for two species, if the bond order is same for two species, the one with lesser number of electrons, the one with lesser number of electrons in ABMO. What is ABMO? Anti-bonding molecular orbital. Right? So the one with lesser number of electrons in anti-bonding molecular orbitals, you can write it as ABMOs, right, is more stable. Right? So if the bond order is same for two species, the one with lesser number of electrons in ABMOs are more stable. I obviously know the stability criteria between your bonding and anti-bonding, right? Bonding orbitals are more stable. So what I'm telling you here is, if the number of electrons in, say, one of the species, like number of electrons in anti-bonding MOs in one of the species is less, that is more stable. So you can look at here. Okay, now here, how many electrons for Li2 1 plus I'm telling, right? How many electrons are there in anti-bonding? There are only 2 electrons here. Isn't it? There are 2 electrons here in anti-bonding molecular orbital for Li2 1 plus, right? Now, how many electrons are there in your anti-bonding molecular orbital of lithium minus? So there are 2 electrons here, and there is 1 electron here, totally making it 3 electrons. Isn't it? Right? So obviously, what did I tell you? The one with lesser number of electrons in ABMO is more stable. Obviously, Li2 1 plus is having only 2, and that is having 3. So definitely Li2 1 plus is more stable than Li2 1 minus. Guys, did you get this point? Everybody got this point?
Yes, sir.
Yes, sir.
Okay, so the thing is, the one which is having lesser number of electrons in ABMO is more stable. That's it. And this has to come into the picture only and only if I have same bond order. Right? Only and only if I have same bond order, or else whatever is having higher bond will have higher stability. Okay, right? Fine. So we'll take one more problem for this. Okay, you're going for O2, O2 plus, O2 minus, O2 2 plus, O2 2 minus. So I have all these things. Okay, I arrange them in the order of bond. Right? I want you to arrange them in the order of bond length. So again, bond length or bond strength or stability, whatever is asked, you have to write the electronic configuration in terms of MOs, find the bond order, arrange them. And guys, don't worry, like you have O2 2 plus is having 14 electrons, right? But don't worry, it is about the original atomic number, right? That means for O2 2 plus also, you have to follow the order for greater than 15 electrons only. Moment you see oxygen, have to go for the second configuration. Okay. Right. Hope you're done. Are you? I'll also start doing. You also do. So go to Okay, so I have done it. You do. Right. Okay, this is here. Right. So for O2, I have 16 electrons. So this would have been the configuration pi star 2px and pi star 2p, pi star 2px1 and pi star 2py1 would have been the end configuration, right? And if you calculate the bond order, number of electrons in bonding molecular orbital 1, 2, 3, 4, 1, 2, 3, 4, 5, so totally 10. Right? And how many electrons in anti-bonding? 1, 2, that is 4 and 6. I'm sorry. Anyways, the answer is 2. So 10 minus 6 divided by 2 is 2. Okay. So now for O2 plus, right? For O2 plus, you can see that the electron is removed from the last orbital. That is your sigma 2py, sigma star 2py. This is the star, right? 0, right? Okay. And if you calculate the bond order nicely, you will get the bond order as 2.5, right? And for O2 minus, you add 1 electron to this, that is pi star 2px2 and pi star 2py1. The bond order will become 1.5. And for O2 2 plus, you removed both the electrons in the 2p star, pi star 2px and pi star 2py. So the bond order will become 3. And lastly, O2 2 minus, I have 2 electrons getting added. So 2 pi star 2px2 and pi star 2py2 will come. So the bond order would have been 1. Right? Done. So how many of you got all this? Or are you still doing?
Oh God, sir.
Okay, nice. Right? So now if you know the bond order, the problem is already done. Right? So now they're asking in terms of bond length. Right? So whichever is having the least bond order will have the maximum bond length. Isn't it? Right? Because stability and bond order are related, bond strength and bond order are related, obviously. So bond order and bond length are inversely related. So in this case, whichever is having the least of all bond orders will have maximum bond length, and that is going to be O2 2 minus. I'll write it here. So O2 2 minus is having the maximum bond length, right? Then comes your 1.5,
O2.
that is O2 minus. And then comes 2 where I have for O2, right? Then I have 2.5 coming for O2 plus, 1 plus, and lastly O2 2 plus. So this would have been the answer. And starting with O2 2 minus, O2 minus, O2, O2 1 plus, O2 2 plus. This is how questions also will be asked in your exams. Okay, they'll give set of molecules. They have to show everything basically. You have to show the, now this and all I wrote like this, commas and all I wrote, you should not write it like this. Everything should be proper. Show the bond order calculation and then write the answer. Okay, this is how you should do. Right. Okay, so the time, still have 5 more minutes. Good. Now we understood bond order, we understood stability, bond strength, bond length, everything, how is it related, all these things we saw. Now, how am I going to predict whether the molecule exists or not? That also I told you, right? We'll be able to predict whether the molecule exists or not. Okay, fine. So that we'll see how are we going to do. Right. So if we have, please take this down quickly. So the thing is, guys, if you understand, if you see closely, I didn't actually calculate the bond order for everything. I calculated the bond order correctly for O2, right? And after that, it's actually very easy for me to calculate the bond order. What I did here is basically, please understand that if at all you say, if you have neutral molecule and you have the bond order with you, right? Say and in this case, you saw that the last electron goes to your anti-bonding orbitals, right? So please understand, if you remove 1 electron from anti-bonding, the bond order increases by 0.5. Please keep it in mind. If 1 electron is removed from an anti-bonding orbital, the bond order increases by 0.5. If you are going to add 1 electron to the anti-bonding orbital, your bond order decreases by 0.5. right? And obviously, if I'm going to remove 2 electrons from anti-bonding, bond order increases by twice of 0.5, that is 1. And if you add 2 electrons to the anti-bonding, you will reduce the bond order by 1, right? And the exact opposite will be for bonding orbitals. If you add more electrons to the bonding orbital, 0.5 for increase will happen for each electron you add. The more and more electron you remove, there is going to be a decrease from bonding, right? If you remove electrons from bonding, there will be a decrease of 0.5 for each electron. So that was the trick which I used. But anyways, if at all, you will not be, you can use it, but anyways, you have to show everything properly and find the bond order. Okay. So anyways, right, for example, you can see here for O2, it was 2, right? And I removed an electron from anti-bonding. So what happened to the bond order? It became 2.5. Right? And again, now O2 minus, now what I did, I added one more electron to the anti-bonding. So it became pi star 2px2. So you can see what happened to the bond order. The bond order decreased to 1.5. Right? So same goes with your O2 plus and O2 2 plus and O2 2 minus. Right? Anyways, so right. So now I told you that we'll be able to predict the molecule exists or not. Now let me take the example of helium. Okay, so helium-2, we'll see what happens here, right? So I have totally how many electrons? 4 electrons, right? So what will be the configuration? Sigma 1s2, sigma star 1s2. Right? Let me calculate the bond order. Bond order is equal to 2 electrons in a bonding orbital, 2 electrons in anti-bonding orbital. The bond order is 0, right? So this is the thing. So whenever you find what do you mean by bond order? That means what? There are no bonds between helium and helium, right? So this kind of things proves that this molecule does not exist. So the thing which you have to remember is whenever you find bond order to be equal to 0, that molecule does not exist. Right? That molecule does not exist. Whenever you find bond order to be 0, there is no existence of that molecule. Because it's understood, because I know bond order talks about the number of bonds. If the number of bonds are 0, that is understood that there are no bonds. So the molecule doesn't exist. Right? And lastly, people, I'll just take 5 more minutes and we'll complete it. Right? So we have, I told you we'll be talking about the magnetic properties. Okay? Actually, what we'll do is it will take some more time. We'll see it in the next class. Okay? So I'll have to explain you why certain molecules are going to repel, why certain molecules are going to attract, why certain molecules have no effect when I bring a magnet. And with the help of this molecular orbital theory, how will I be able to predict? And we have to see the secondary types of bonds: hydrogen bonding, dipole-dipole, van der Waals forces. All these things we'll be seeing next class. So next class, your thing is getting over. Okay, your chemical bonding is getting over. So the next chapter would be gaseous state. So it is no more going to be this what to say, conceptual things. It is going to be problematic. So many numericals. Again, I think for the next 3 chapters, gaseous state, equilibrium, and your thermodynamics, it is conceptual obviously, but it will be more of problems oriented chapters. Okay, and after that we'll be going for organic, right? For it, that is like if you ask me which is the most interesting part in chemistry, for me it is organic. But again, people will say different things. For me personally, organic is the best thing. So anyways, we'll see all that, right? Fine then. So until then, we'll see you guys. Thank you. Bye bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.